log loss or cross entropy is another metric you can use for probabilistic models. Now what log loss is going to do is going to take into account uncertainty of your model's predictions. This is something that accuracy does not do. So the equation for log loss is here. So notice where it gets its name, the log. There was a typo in the notebook, but I corrected it there. It should be 1 minus p as opposed to p. All right, so let's define these terms here. So y is the label of the observation. Let's consider a binary situation, 0 and 1. So we have class 0, class 1. So y is either 0 or 1. P is a probability that the observation belongs to class 1. And then we sum them all up for all our observations. That's our log loss term. So let's consider the example in which the observation is 0. So if the observation is class 0, we want our model to report a very small probability for this observation to belong in class 1, since indeed is in class 0, not class 1. So we want this probability to be small. So if y is 0, the first term is gone. So let's only focus on the second term here. 1 minus y times log of 1 minus p. So 1 minus y is just simply 1, since y is 0. So what's left is log of 1 minus p. We discussed before, we want our model to report a very small probability. So we have the log of 1 minus a really small number. That's going to equal to log of a number that's very close to 1. So what is the log of a number that's very close to 1? What is the log of 1? Log of 1 is 0. So log of a number that's very close to 1 is going to be very close to 0. So notice our loss here is 0, which makes sense because if the observation is class 0, we want the probability that the model reports to be in class 1 to be very small. Let's consider the other situation in which the observation is class 1. If the observation is class 1, we want a very high probability that the observation is in class 1. In that situation, we only have the first term here, y times log of p. We don't have the second term here. Since y is 1, so 1 minus 1 is 0. And this cancels out. So we have y, which is 1. So simply left behind is log of p. Now we want our probability to be very close to 1. So the log of a number that's very close to 1 is a number that's very close to 0. So our loss is very small. Let's visualize. Let's go ahead and visualize our plot here. So this is our log loss curve. So we're only considering when y is equal to 1. And notice, as we become more certain that our observation is in class 1, and indeed is in class 1, the loss term is going to drop. It starts dropping. And this makes sense. Let's talk about the importance of this log loss metric. What this log loss metric is saying is that, yes, it's important that we do properly classify the image, whether we say it's in class 0 and 1, but it's also very important that we are very certain in these predictions. So as we become more and more certain in the right answer, our loss drops. So if we use this as a metric to optimize as our cost function for our classifier, this is a function we want to minimize, figure out what are the best coefficients, the best model parameters. They're going to yield a very small log loss. What's going to result is a model that's becomes more and more certain about its predictions. And on the other hand, if the model is very certain that it's in class 1, but indeed is in class 0, then you're going to be hurt. The model is going to penalize you for that incorrect certainty. So you're very certain in the wrong answer, that's going to have a greater error than if you're not very certain in the wrong answer. As well as if you're very certain in the correct answer, if you're very certain about the correct answer, then that's going to manifest itself by a very small penalty. So that's the power behind the log loss. In fact, the log loss is used as a cost function. A lot of probabilistic models. We'll discuss one just in a bit. Some classification models are going to return to a probability of the observation to belong to a class. There are other ones that will just return to you, okay, this is in class 0 and class 1, but other ones, called probabilistic classification models, will return a probability. Going back to the case study of image classification, we have two classes, whether something is a cat or a dog. The model can return some probability it thinks that this image is a cat. We give it an image, and the model says, okay, I'm 75% certain it's a cat, or 35% certain that it is a cat. Now, given these probabilistic models, let's say it says, okay, this image is 75% chance of it being a cat. Should we go ahead and say that this image is a cat if the model says it's 75% certain that it is indeed a cat? Or should we say it's a dog? What do you guys think if we say it's 75%? The model says 75%. Well, it's logical to assume, or to make the judgment that since it's greater than 50%, we should go ahead and say that this image is a cat as opposed to a dog. But what if I want to be very precise or be very certain that whatever images that run through my model, that if they say it's a cat, that it's really indeed a cat? That 75% perhaps isn't high enough for me. For whatever application I'm doing, it's not as high enough for me. And I'm going to say, unless that probability is greater than 90%, then I'm going to say it is a cat. If it's less than 90%, I'm going to say it's not a cat. I want to be very certain. I want to be very precise in my observations, in my predictions, in my classifications. So what we see here is that we don't have to use this 50% threshold. We can use a different threshold. We can use something higher. Regarding this threshold, you can think of it as a knob. How do you think this threshold, modifying this threshold, how do you think it's going to affect concepts like precision and recall? Metrics like precision and recall. In other words, if we have a very high threshold, if we increase our threshold, how will that affect precision? Is our precision going to increase or will it decrease? Same thing with recall. If we increase our threshold, how will that affect recall? Well, let's think about it. As you increase the threshold, you're basically saying, I want to be very certain that this image is a cat before saying it is a cat. I want to be very certain, very precise. So my precision increases. The number of false positives drop. But guess what? My recall is going to suffer. There's going to be some images out there, a lot of images out there that are cats, but since I have a high threshold, I'm not going to label them as cats. They go unidentified as cats. I didn't capture them all. I didn't recall them all. So my recall is going to be very low. On the other hand, if it becomes very important for me to make sure that any image that comes in here, if it's a cat, I label it as a cat, then I can drop my threshold. I can drop my threshold to be very small. So because my threshold is very small, I only need a very small amount of certainty to say something is a cat or not. So I'll be able to identify, I'll be a pretty good chance to identify all the cats, all the images of cats, but at the cost of saying things that are indeed cats but indeed are not cats. So I'm going to have a lot of false positives in that case. So you can see this idea of the trade-off between precision and recall. We can see that trade-off directly by considering the threshold for a probabilistic model. Now let's visualize this trade-off. We understand there's going to be a trade-off. We understand why there's going to be a trade-off, but let's visualize it. So we're going to generate some data. Do there. Make sure I run everything up above. Okay, so I have my data there. And let's go ahead and calculate things like precision, recall, and the F1 score. Remember, the F1 score is a harmonic mean between precision and recall, and it's a good metric to use if we have no preference for precision and recall. It's a harmonic mean between those two metrics. Let's visualize our results here. So we have is threshold on one axis and those three metrics on the y-axis. As we discussed, as we rationalize, as we increase our threshold, I'm becoming very picky. I want to be very certain that this image is a cat. So our recall is going to drop, but our precision is going to increase. If we look at the graph here, it appears that around 36 threshold, so 36%, if we set that threshold, that will achieve the highest F1 score. One thing that you should keep in mind here is that any probabilistic model can achieve any arbitrary level of precision and recall just by adjusting this threshold knob, just by adjusting this threshold for our model. So when we're talking about probabilistic classifiers, we need a single metric that is not dependent on threshold. Because let's say you have a model, a probabilistic model, and you say, I want it to have 95% precision. No problem. As we see here in this graph, we can adjust the we can adjust the threshold to achieve that level of precision. What if we wanted to have a very high recall? Well, we can just lower down the threshold and achieve that very high recall. But guess what? At a large cost of precision and vice versa. So we need a single metric to use to evaluate, or use a single metric to use for our cost function or optimizing our probabilistic classifiers that are independent of threshold. That is a measure of this trade-off. There's going to be a trade-off between precision and recall. There's no way around it. There's going to be that trade-off. But ideally, this trade-off isn't very severe. It's a very small trade-off. You don't lose as much. So let's talk about how we can get a metric that encompasses this trade-off as a measure of how severe this trade-off is between precision and recall. So let's go ahead and visualize our results in a different format, a different way, a different manner. In this case, we throw a precision. We're not plotting precision. Instead, we're plotting precision versus recall. So precision on the y-axis, recall on the x-axis. Same behavior we saw before, makes sense. As recall increases, precision decreases. Now we don't want this decrease to be as severe. So you can think of this drop, this level of drop, as a measure of how severe the trade-off is. So if I go ahead and sketch two plots out here, so this is the same axis. So I have precision here, and I have recall here. And let's say these two curves, the black and the red, represent two different models. Two different models with different levels of precision recall trade-off. Given the behavior of these two curves, what do you think is the better model to use? Which model has a less severe trade-off? Is it the black or is it the red? We want to go with the red model because if you look at it, this represents a less severe trade-off. As you increase the recall, yes, precision drops, but not as much as the black curve, the model represented by the black curve. So the red model is the better model to go with. Now we did this visually, right? We just plotted these two graphs, these two curves, and we can say which one is better, which one is best to use. But can we do it a different way without visualizing the precision recall curve and picking it out? Can we generate a single value, a single metric that represents the red curve and the black curve that we can easily compare? What would be a good metric to use? A single value that encompasses this behavior. Well, let me throw this at you. Between these two curves, which one has a greater area under the curve? We would integrate from 0 to 1 recall. Which one will have a larger area? Is it the black or is it the red? The model represented by black or the model represented by red? We look at it. So visually we know that the area under the curve for the red curve, for the red line, the model represented by red, will be larger. So the less severe the trade-off between precision and recall, the larger area under the curve. And what are the bounds for this area under the curve? So note at the very least, we have 0. But what is the value that it cannot exceed? What would be the area in the curve if we had a model that for some reason is very magical, is magical and has no precision and recall trade-off? What would be the area in the curve for that ideal model? In other words, a model that just doesn't drop precision as you increase recall. Magical model. You won't have this in real life. You have some trade-off, but what would be the area in the curve for the blue one? It would be 1. So the nice thing about the area under the curve is that it encompasses this trade-off between precision and recall and is bounded between 0 and 1. So that's what's the AUC. Every time you see AUC, that's just a shorthand for area under the curve of the precision recall plot. Now, there's another way you can visualize precision recall using what's called the receiver operating characteristic curve. And that curve is it's going to plot the true positive rate, which is another word for recall, versus the false positive rate, which is equal to 1 minus the negative rate, also called the specificity. So you can plot it that way and also generate area in the curve. It's a very similar metric. But it's best to use the precision recall area of the curve when the positive class is rare or when you care more about the false positives than false negatives. So we can play around with these two metrics. We have functions for them. They accept the recall and precision. The other one, you can pass your predicted values and the true values. So let's go ahead and plot. Let's go not plot, but let's go ahead and print out these two metrics for area in the curve.